In the last couple of lessons, we obtained the velocity components along the x-axis and along the y-axis, all along the path. Now let's put these two together in this lesson, and that way we will have the resultant velocity at any given point in time. Before we get into the animation, just to recap, the x component of velocity, or Vx, does not change, it remains constant throughout the flight. But the y component, Vy, or v sine theta, goes down to 0 just as it reaches the top, and then increases again on its way down. So when we play the animation, the length of Vx does not change, but the length of Vy will decrease on its way up, and then increase on its way down. So now let's watch the animation. As you can see, Vx does not change, but Vy, which was initially pointing upwards, it went down to 0 and then increased again in the downward direction. Now let's watch this at various positions. Vx, which is v cos theta, remains the same throughout regardless of time. So as the projectile moves up to the highest position or moves down, you can see that Vx does not change at all. It always remains the same regardless of time. But Vy, which is v0 sine theta minus gt, is time dependent. So on its way up, we see it decreasing. And you can see the size of the arrow decreases on its way up. Now the net velocity is the resultant of Vx and Vy. The net velocity v is always tangent to the curve. And you can see that here as the projectile moves, v is always tangent to the curve. Since Vx remains constant and Vy decreases on its way up, v, which is the resultant, would also decrease on its way up. At the topmost position, Vy goes down to 0, so the net velocity in this position would be just Vx or v0 cos of theta. There would be no y component here. So this is a difference between a ball that is thrown up vertically and a projectile. While the ball had a 0 velocity in its topmost position when it's thrown vertically, a projectile will always have some speed in its topmost position, and that is because it has the x component, which is v0 cos of theta. As the projectile begins to fall down again, Vx continues remaining the same, whereas Vy begins to increase. So therefore, the resultant v also begins to increase on its way down. Also, we have been able to mathematically establish the x displacement and the y displacement at any given time. The x displacement is v0 cos of theta times the time, t, and the y displacement is v0 sine of theta times t minus half gt squared. If we want a mathematical expression for the net velocity, it would be the square root of Vx squared plus Vy squared. And this would be changing at every point along the path, since although Vx remains constant, Vy keeps changing. the instantaneous angle theta made with the horizontal would be the tan inverse of Vy over Vx. Don't confuse this angle with the launch angle, which we had also earlier called as theta. This angle would be changing throughout the flight, so at any point along the path, since we know Vx and we know Vy, we could always compute the angle at that point. With this, we are in a position to find the displacement of a projectile and its net velocity at any given point in time or at any point during its flight. In this lesson, we have learned to find the net velocity of a projectile at any point in its flight. We know the x component and the y component of the velocity, and in order to obtain the total velocity or the net velocity, we use the square root of Vx squared plus Vy squared. Also, we are able to find the direction of the net velocity at any point. Since we know Vx and Vy at all times, the instantaneous angle made with the horizontal is the tan inverse of Vy over Vx.